Hey folks, how's it going? This is Mr. Murray coming to you with a video on probability, and this is going to be my first in a sequence of videos on probability. Now, this is just such a really awesome mathematical topic, and one that we could honestly discuss for a long time. Some students in college basically could spend an entire year, 2 semesters, right, studying probability, and if you add in statistics on a really deep level. It is such a really interesting and really relevant topic in mathematics. Here are some ways that I thought I would share with you that probability is used in everyday life. There's so many applications of it. One application that's really cool is bioinformatics and biostatistics. Using statistics and now with the power of computing and high-powered computers, we can actually predict how, using like a chemical formula, how the actual atoms will be arranged in that formula to a very high degree of accuracy, using probability related to how those given certain features, how those atoms could possibly be arranged, right? So it has to do with probability. What's the probability that this atom could be in this particular place? One really common place they use probability is in automotive, health, and really any kind of insurance. What's the probability, if you think about the fact that someone's been in an accident, that they're going to get in an accident again? What's the probability if someone parks in Milton versus in somewhere like Dorchester or Mattapan or Brockton or someplace like Weston or Newton, or I don't know. You could think about it. What's the probability that their car is going to get broken into based on the crime that happens to exist in that particular area? Those are things that are going to then impact the probability that that company is going to have to pay money related to your car. So then in turn, that's going to be used to figure out how much to charge you so that they can make a profit. Billions of dollars, I'm telling you, are made. And if you decide to do what's called actuarial science, where you go into math related to insurance, with only a 4-year degree, you can kind of get started with that. You can make a significant amount of money doing something like that. Okay. Here with vaccines and drug manufacturing, probability is used a lot. If you think about like vaccines and tests, we have what's called a false positive and a false negative rate. So what's the probability if I get the result, yes, this test came back positive, that positive was actually a mistake? Sometimes, believe it or not, tests are wrong. And that's why there's called, I don't know if you've heard about this, what's called a false positive rate. The rate at which the test will tell you you're positive, but you're actually not. Similarly with a negative, the probability that the test will tell you you're negative, but you're actually positive. And that's something to consider, because if I want to know, if I get a result, what's the probability that that result was actually correct? If it's very low, then the test was pointless, right? I want to make sure I'm getting accurate information if I'm going to be making decisions on the basis of those results. Similarly with drugs, if you think about drugs, one of the big things that drug manufacturers are concerned about is the balance between a drug that will have benefits to you and one that could seriously harm you. What's the probability if someone takes this drug, they're going to have side effect A? Okay, and then you could weigh into that. I don't know if you've seen commercials. Do not take this if you are taking this medicine or if you have this condition. So then what they've probably done is they said, given that they've got this condition, the probability that they are going to experience a very dangerous reaction is high, right? So they've calculated some number, okay? And finally, and this is actually something taken out of my undergraduate thesis when I was at UMass Boston, I used probability to model a network of different things interacting with each other. So the little blue dots you see are what are called microRNAs, and the orange dots you see are what are called competing endogenous RNAs. And what's happening is all of the orange dots are competing to interact with the blue dots. And based on certain probabilities, the probability that additional levels of orange will be generated, right? Occasionally orange things will, die off. And then there's certain probabilities that each one of these orange nodes will interact with each of the blue nodes. What I can do is I can do what's called a stochastic simulation and model over time what the network's looking like. So if I want to study this particular P10, which happens to play a role in suppressing tumors when it comes to cancer, if I can get a really good sense of how this network is functioning using things like probability, assuming I had a complete network, I could try to develop drugs that would help skew this network to produce more P10, which would in turn lead to reduction in cancer. So all different kinds of uses. I know I've spent a while talking about this, but I just want to share with you how amazing probability is, how widespread it's used, and honestly how powerful it is. Okay, so enough of me talking about that. I'm going to jump into an introduction today, right? The name of this video is Introduction. And so I'm going to start with the most basic level of what probability is. And so in order to do that, I need to start with talking to you guys about set theory and sets. So if we think about a set is just a collection of non-repeated, that is distinct objects. We've actually seen this. We talk about it a lot in Course 1 Honors when we talk about our Course 1 CP, when we talk about like domain and range. Sometimes when you have a discrete graph, that's a bunch of points, right? If you've got a discrete graph, we use a set and we list all the numbers out. And so that's all a set is. It's just a collection. And so here's a set. We have a little like a boomerang, a little trapezoid, all different kinds of shapes in our set. Okay? Each thing in a set, each individual member of a set, so to speak, is called an element. So this is an element. This shape is an element. This shape is an element, and so on. There are special kinds of sets. An example of a set we've seen is the set of real numbers. This year, we saw the set of complex numbers, a plus bi, right? In your life, you worked with all kinds of sets. Positive numbers, right? 1, 2, 3, 4, 5. Or sometimes called the counting numbers. Negative numbers, only the negatives. The integers, whole numbers. All kinds of sets of numbers. We usually have been, that's the context usually, but it doesn't have to be numbers. Another special type of set is called the empty set. And the empty set is just simply the set that doesn't have any elements inside of it. It's empty. It's often denoted using this symbol. I've talked about this symbol in previous years. I usually talk about it with domain and range. And when I say, or not domain and range, I usually talk about it with like maybe sometimes increasing or decreasing. Sometimes I talk about it with positive and negative. So maybe there's a function where that's never decreasing, right? An exponential function sometimes never decreases. So there are no x values. If I was to list the x values, there would be no x values where it is decreasing if it always increases. So I would use this empty set to represent that set of applicable values has nothing in it. Sometimes people also use the curly bracket and the curly bracket, and then there's nothing inside of it to indicate it's just a set, but it's empty. There's nothing in it. And finally, there's a notion of a universal set. And the universal set contains all elements we would want to examine. So sometimes what you can have is a set that sits inside of another set, and I'll talk about that in a minute, and that other set will be the universal set, some like wider ranging number of things we might want to look at, but we might just want to zoom in to a particular piece. So imagine this is sitting inside of another thing, which we often call U for universal, and then there's some more shapes outside of it. Maybe like I can see we got a green square, maybe a black square. Maybe I've got like a black diamond, okay, etc. Here's a little star, okay. So the universal set has some other things, but what I'm focusing in on now is just this set that's in this oval here, okay. All right, so here's some examples. Set A is the list of prime numbers that is less than 10. So notice the use of A. We write A is equal to curly brace. So we're going to do, see how I do an S and then a backwards S. Shout out to my 5th grade teacher for teaching me that, because I've been doing it now, as he reminded me in the past few months. I've been doing that for 20 years. So it definitely takes some experience. I need prime numbers less than 10. So a prime number is a number greater than 1 that is divisible by only itself and 1. So those numbers would be 2, 3, 5, 7. Sometimes we use the notation n of A to talk about the number of items or elements in set A. Here we would say 4. Another way you would write this is A in absolute value, and that means the cardinality of A, which is essentially how many things are in A. Okay, set B is the set of even natural numbers less than 10. In other words, when you think natural numbers, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, whatever, and so on, right? The counting numbers. They're sometimes also called the natural numbers, whereas the whole numbers are the natural numbers, but you also put 0 in there. Okay, so even means it's a multiple of 2. So I've got 2, 4, 6, 8. I cannot include 10 because it's less than. It's not less than or equal to. And I actually shouldn't be calling this A, because this says I should be calling this B. So the cardinality of B, or the number of elements in B, is equal to 10. You can use either notation. Set C is the set of natural numbers less than 10 that are multiples of 4. Okay, so the multiples of 4 less than 10 that are also natural numbers, they have to be at least 1, are 4 and 8. Notice if they didn't say natural numbers, that would put us in a pretty interesting predicament. And finally, the universal set is the set of all natural numbers that are less than 10. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9. It depends upon how you define the natural numbers. Some people define the natural numbers to include 0, and other people don't. I personally define the natural numbers to not include 0. If you do, that would kind of change this. 0 would technically be a multiple of 4. It's 4 times 0, so you'd have to include that in set C. It would also technically be considered an even number, because any multiple of 4 is also a multiple of 2. So just worth considering. Okay, sorry about that if there was any noise there. So basically, what I'm going to do is this. I'm going to now talk to you about some things that we might notice here. What I notice here is that there's some similarity. So everything here is within U. Notice that every single one of these, if I take a look at their numbers, they'll also be found in U, right? All 4 of these are in U. All 4 of these are in U. Both of these are in U, okay? So any number that's in A, B, or C is also in U. Another thing I notice is that if you take a look at A and B, there's some overlap, right? A and B both have a 2, and that's it. Also, if you take a look at B and C, there's even more overlap, right? The 4s and the 8s. So if you think about it, if I was to take a look at where these two sets intersected, right, where they lined up, where they were equal, in a sense, right? These would have a 2 in common, and these would have a 4 in common. Just like an intersection is a one place that's on both roads. They have both of those roads in common. I could also look at what happens when I take two sets and just put them together. Just like I take two people and bring them together in a union, I can take two sets and bring them together and see, hey, let's take all of our stuff and pool it up. And if anything is in either one, we'll bring it together. Okay, and then finally, I could ask, what is this set missing? What is in the universal set that I've left out of A? And that is something else. So let's take a look at some of these ideas right here. So we have a subset, an intersection, a union, and a complement. So a subset is a set of another one, so that every element in the subset is also an element in the bigger set. So let me give you an example of that. If I was going to draw a bunch of numbers, so like 2, 6, 8, 13, 5, 3, okay? And then I took this 2 and 6 off to the side. Maybe I said I only want the numbers that are even and less than 8. So 2 and 6 would be, and that's just like arbitrary that I chose those. Okay. So any set that takes elements of another and pulls them away is considered a subset. We see this a lot when you do like statistical surveys. Maybe you want to take a look at the subset of people who are under 25. A common thing we do in TV sometimes, I think there's like an 18 to 26. Like we want to know, let's take a look at only the people who might be 18 to 26, right? That subset of the population. So we're taking all the people, but we're only grabbing those 18 to 26-year-olds out of it. An intersection of sets is the set of elements that are in both things at the same time, okay? So if I have this common Venn diagram, that's where they overlap. So let's say I've got 1, 2, 3, 4, and 2, 4, 6, 8. 2 and 4 would be in the intersection because that's where both sets overlap. Please note the use of A, B. So it's okay. The notation's really important. The union is all of the elements that are in either one or the other. So the union is just saying, hey, let's pool our resources. So if I've got 1, 2, 3, 4, and 5, 6, 7, 8, the union is everything that's in either set. So it would be 1, 2, 3, 4, 5, 6, 7, and 8. If there's numbers that overlap, you only write those numbers one time. Because remember, a set never repeats. Finally, I'm not going to draw a picture of this, but I'll just tell you the complement, and it's written either with a C for complement or the little squiggly tilde, is just everything that's not in the set but is in the other. So my example is if U is equal to the integers, and remember the integers are the positive and negative whole numbers, and 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and onwards, -1, -2, -3 and that onwards, and 0. So if I say A is the positive, if A is the positive and 0 integers, so that is 0 and all the positive numbers, then A complement is equal to the negative integers, right? Because A complement is everything that is not in A, but is in the overall set, right? Everything is the integers. I'm saying take all of that and throw out 0 and the positives. And so what you'd be left with is the negatives. Notice how if I bring these together, though, if I take A and I take its union with its complement, I get everything. That is to say, if you take everything that is in A and everything that's not in A and you bring them together, you get everything. And maybe that's something that might seem obvious to you, maybe not. And either way, that's fine. So here's a little problem for us to do, and I thought maybe we could work through this together. So we're given three sets. We're given A, B, and U. A contains the numbers 21, 23, 25, 27, 29. B contains the numbers 21, 24, 27, and 30. Now, A and B are subsets of the universal set U, which is 20, 21, and basically all the whole numbers up to 30. Okay, so you can imagine a world where we've got 20, 21, 22, 23, 24, 25, 26, 27, 28. All right, you can imagine this. And then A and B are essentially subsets of this. They contain the numbers in there. So here's B, for example, 21, 24, 27, and 30. Let's see if I can, I don't know if I'm going to get the same kind of look. Yeah, I don't know if I'm going to get the same kind of look. So I can get 21, 23, and then, see, I'm not going to get them to overlap pretty well. But you get the idea, right? These are just essentially subsets of everything. So what I want to know is these things. What's the intersection of A and B? Also known as, remember, A intersect B. What's the complement of A? What's the union of A and B? A union B. And we talked about this. If this seems familiar, we talked about this. I think we talked about both of these, but we talked a lot about this with analysis. The complement of set B, which is BC, or remember, it could be squiggly B. So this could be also squiggly A. The number of elements in A, which is NA, and the elements in B, which is NB. So actually, I'm going to actually take this in a you try direction. So here's what I want you to do. I want you to pause the video. I want you to, for 1 through 4, give me the squiggly brackets and write out the actual sets. And then in 5 and 6, give me the number of the elements requested. So pause the video, try this, then when you're ready, unpause, and you can see what I got. Okay, so 1, the intersection of A and B is the items that are in both A and B. So A and B both contain a 21 and a 27. So A intersect B equals 21 and 27. Okay, now 2, what's the complement of A? The complement of A is, remember, everything that's in the universal set, but which is not in A. So for example, 21, for example, let's work backwards. I like to start with the universal set. So I'm going to look in the universal, is it in A? So 20 is in the universal, it's not in A. 21 is in A. 22 is not in A. 23 is in A. 24 is not in A. 25 is in A. 26 is not in A. 27 is in A. 28 is not in A. 29 is, and 30 is not. So if you take a look at A, you'll notice none of these are in there, but they are in the universal set. Moving on to 3 now. So I need the union of the sets. So that is to say A union B. So what I'm going to do is I'm going to look at them, and remember, you never repeat. So I'm going to go least to greatest. So I'm going to start with 21, only one 21. Because 21 comes up twice, you only write it once. 23 is next, because it's in at least one of them. It's not in B, but that's okay, because it's in A. 24 is in B, so that's okay. 25 is in A. 27 is in both. 29 is in A. And 30 is in at least B. Just as a quick aside, there's something called A XOR B, which is called the exclusive OR. And the exclusive OR, and you don't need to know this, but it is interesting, and it comes up in computer science. It's just the OR, the union, but if it's in both, it doesn't count. So what I mean by that is it would be this, but we throw out the intersection. So that is to say, it would be 23, 24, 25, 29, and 30, right? So it's just subtracting out the intersection. And there is actually subtraction with sets, believe it or not. The number of elements in, real quick before I do the elements, the complement of B. Everything that's in B that is not in, everything that's in the universal set that is not in B. And I'm going to use the diagram to help me. So 20, 22, 23, 25, 26, 28, and 29 are not in B. And if you think about it, you'd expect the set to be relatively large because B does not have very many things in it. So therefore, there should be a large number of things that we get if we look at the things that are not in that set. Okay? Finally, the number of elements in set A, I'll just write it on the line. It's because it's just a number. A has 5 elements in it, and B has 4 elements in it. So n of A is 5, n of B is 4. So please make sure you understood that, so you got a good, strong sense of set theory, and then in a moment I will move on to the next part. All right, so a probability experiment is what we're going to focus on now, because now we need to define what is probability, and then we're going to actually start calculating some. And if this is a review for you, amazing. That's all right. That's good. But if not, that is perfectly okay too. So a probability experiment is any activity that involves chance, right? The chance that something will happen. And I'm sure you've seen a lot of these throughout your life. Each time we carry out a probability experiment, it's called a trial. The flip of a coin, the roll of a dice, the selection of a card, pulling the lever on a slot machine, right? Starting that trial, right? A spin. So when we work with probability, we're interested in a couple of things. One, the event, also sometimes denoted E, and 2, the sample space, more commonly denoted S. Okay, so the event, if we think about rolling a dice, if we think about picking a card, if we think about spinning a wheel, and we're told this is what we're trying to get. So if you spin the wheel and you get at least a 2, then you win. The event is the set of things that we might be looking to get. So if I say, if you roll a dice with 6 sides, and I want to know, my experiment is, what's the probability I'll get a number more than 3? It would be the numbers more than 3, because that's the things that I'm looking to get. The sample space, on the other hand, is the superset of E, and it's the set of all possible outcomes that could possibly happen. So what I mean to say is, if I was to roll a dice with 6 sides, the sample space is 1, 2, 3, 4, 5, and 6. The 6 possible outcomes that I could get from rolling that die. Note that the event is always a subset of the sample space. That's why I said the sample space was a superset. The event always contains elements from the sample space, right? So, and it could contain the whole thing, in which case the event is completely always likely to happen, or it contain none of them, which means it would be never likely to happen. Here's an example. So suppose I'm going to randomly select an egg from this carton here. So these are 12 eggs, right? I'm told that randomly eggs have been put in there such that 3 are rotten and 9 are perfectly fine. My experiment would be selecting a good egg from the carton. So I'm going to, at random, take a good egg. The trial is going to be simply one trial, the actual selection. I'm going to pull that one egg, and I'm going to be looking for the probability in that one pull. The event is the 9 good eggs we like to get, right? So because I want to know, I'm going to probably ask, what's the probability more likely that we get an egg we want? So the event is going to be the 9 good eggs we like, because that's the desired outcome. And the sample space is the entire carton, because that's the 12 eggs that we could possibly select. So again, you can see the sample space is everything we could get. The event is the things that we actually want to get for the purpose of this experiment. If I had asked you the probability of selecting a bad egg, then it would have been the 3 bad eggs would have been the event. So you just got to be careful when you kind of break this stuff down. So the theoretical probability that an event within a sample space will occur is defined as the number of elements in its sample space, in its event space, divided by the total sample space. Sometimes, and this will be written in the textbook as well, you'll see them write NA, and A will be understood to be the sample space. But what it matters is, if you think about it, the probability is the number of outcomes we want over the number of outcomes that could possibly happen. And it's always written in either one of two ways: a decimal going from 0 to 1, or a percent going from 0 to 100. Okay? So this is the definition of theoretical probability. And remember, n means the number of items in the set, or elements. So here's my example. So suppose I've got 3 rotten and 9 normal eggs in this carton. So here's 2 events. 1 is selecting a bad egg, is A. B is selecting a good egg. And the sample space is S, which is the carton of 12 eggs, right? Because that's the entire 12 eggs you could have chosen from. The number of elements in the number of elements in the bad eggs is 3, right? The 3 bad eggs. And for B, it's 9, the 9 good eggs. Of course, the sample space is the full dozen, or 12 eggs. So the probability of a bad egg is just the 3 bad eggs out of the 12 possible, which is 25%, or 0.25. And the probability of selecting a good egg at random would be 9 out of 12, which is 75%, or 0.75. Now keep in mind, this example was intentionally designed to be very oversimplified, just to give you the idea of how we're even doing this process of getting probability. Okay, so here's like an application, an interesting gamble. So I have a game for you. You're going to pay $5 and roll 1 6-sided die. If you roll an even number less than 6, you win $20. Otherwise, you win nothing. Find the probability that you win. So let's define A to be you get number less than 6. B is going to be, you know what? I'm going to do this another way because I want to show you another way people do this. So first of all, sometimes people write it like this: P less than 6. So when we talk about this, what I'm going to do is I'm going to list the number of things we could get that are less than 6 over the total possibilities. So let's take a look. So first of all, I'm going to start with the sample space. When I roll one die, what could I get? I could get 1, 2, 3, 4, 5, or 6. But I want the numbers that are even, and I want the numbers that are less than 6. So first of all, less than 6, 1, 2, 3, 4, and 5 are less than 6. So there's 5 numbers here. There's 6 numbers in total. So we get 5/6. And I would actually accept that. You could do it. You could leave it as a fraction. I would actually be okay with that third representation. You could do it as 0.83. You could do it, or about 83%. Okay. So I'll amend what I said before. If you want to leave it as a fraction, you're fine. I'm just saying generally they're represented as decimals or percents. All right. Even. What's the probability of being even? So that would be, well, so the even numbers on the dice would be 2, 4, or 6. Whereas, again, all possibilities are 1, 2, 3, 4, 5, and 6. So the number of ones we want, 3, the number of ones we could possibly get, 6. So this is equal to 50% or 0.5. Now here's where it starts to get interesting. What about the probability that we're less than 6 and even? Okay, so let's take a look at what set I could have. Less than 6 and even. So notice the 2's overlap and the 4's overlap. So 2 and 4 are only acceptable candidates because those are the only ones that are in both. So we have 2 that could be good over 6 that we could possibly get, and that is 1/3 or approximately 33%. So you have a 33% chance of winning. What's the chance that you don't win? If you have a 1/3 probability of winning, what's the probability you lose? Well, think about it. It's 2/3. And what's another way to get 2/3? From 1/3. Notice that, interestingly, if you take 100% and you subtract the percent of winning, you get the percent of losing. That's an interesting concept. Okay? Finally, notice that less than 6 or even, okay, that would give you 1, 2, 3, 4, 5, and 6, because every number on a dice is either less than 6 or even, right? Because less than 6 provides 1, 2, 3, 4, and 5, and then even comes in and adds that 6 to fill in the rest. So that's 6 out of 6, or 1, or 100%. So this is why it's an and game, not an or game. Okay? So please make sure you understood what I did there. Pause if needed, rewind if needed, and then in a moment I'll move on to the next concept. Alrighty, folks. So here I'm going to do a little bit more practice with probability. So your grocery basket contains, and by the way, if you feel comfortable, you can feel free to skip using the comments below, using the details below to the next concept. So your grocery basket contains 1 bag of each of the following items: oranges, green apples, green grapes, green broccoli, white cauliflower, orange carrots, and green spinach. You're getting ready to transfer your items from your cart to the conveyor belt for checkout. Event A is picking a bag containing a vegetable first. Event B is picking a bag containing a green food first, and all items have an equal chance of being picked first. That is important to technically state that. So our sample space is all the possible vegetables that we could pick out. We're going to pick something in there, or fruit or whatever. That's basically our shopping cart. Think about the S as our shopping cart. So there are 1, 2, 3, 4, 5, 6, 7 different things that we could take out of our shopping cart. Okay. Event A is picking a bag containing a vegetable first. So what are our possible vegetables? So broccoli, we could have picked a carrot, or we could have picked spinach. So, and if you think about it, there's 4 items that are vegetables. There are 7 items total, so we get 4 sevenths. How about the things where there's overlap, A and B? So A is picking a vegetable first, B is picking a green food first. So first of all, let's start with vegetables. So vegetables, we'll start with broccoli. I'm going to abbreviate here: cauliflower, carrot, and spinach. So everything in A is in there. And now let's start to drop some stuff in from B. And B is the green foods. Now the grapes we know were green. We were told that. And the apples we were also told were green. So it's 1, 2, 3, 4, 5, 6. 6 items in there. Notice how the oranges are left out. I think we can safely assume that the oranges are orange. So I think that's why they didn't say oranges. Okay, so the probability of selecting either a vegetable first or a green food first is the number of items in the intersection over the total possible things we could have chosen. And that is 6 out of 7. And that's what we could do. So see, sometimes it is okay. So again, I just want to clarify. Oftentimes, as final answers, people provide decimals or percents for probability, but it doesn't mean that you can't necessarily provide a fraction. That can be okay as well. So I'm okay with you giving fractions, especially in circumstances where you have these decimals, where if you do leave it as a fraction, you're going to get a more accurate answer than if you try to provide a decimal approximation. Okay, anyway, what about the intersection? Where do they overlap? So remember, the green foods first, we should probably state what those are because we've said A but not B. So B is picking a green food first. So B, we want the green foods. So that's apple, grape, broccoli, spinach. Apple, grape, broccoli, spinach. Okay? So what's in both? What is in both A and B? Let's take a look. Spinach, broccoli's in both. And spinach is in both. And so the total number of items here is 2. So what's the probability that our first item we pick is a green vegetable? That's what those are, right? The greens that are also vegetables. So it's going to be the number of items that are green vegetables out of everything we could have chosen. And that's going to be 2 out of 6 or 1. Actually, not out of 6 because there's 7 items in there. So it's going to actually be 2 out of 7. All right, last one here. I'm trying to figure out what they're getting at here. I'm going to do the probability of a complement. So that is to say, the probability I do not choose a vegetable bag first, right? Not A is not happening. So that's the number of items that are in the cart but are not A, and over the total number of things in the cart. So we've got 7 possible things. What is not in A? So I go back to S. Orange is not in A. Apple is not in A. Grape is not in A. Broccoli is, cauliflower is, carrot is, spinach is. So 3 out of 7. There's a 3 out of 7 chance that this thing you choose is not an A. Similarly, with B, right? There's 7 things you could pick. Out of those 7, how many are not in B? So orange is not in B. Apple is in B. Grape is in B. Broccoli is in B. Cauliflower is not. And carrot is not. Interesting. So you have an equal chance of choosing something that is not in A as you do as something that is not in B. Cool. All right, folks, time for you to try. So here's the situation. We have the numbers 1 through 30 written on slips of paper that are then placed in a hat. Students draw a slip to determine the order in which they will give an oral report. Event A is being one of the first 10 students to give their report. Event B is being a multiple of 6. If you pick first, calculate each of the indicated probabilities. Okay, the reason we need to pick first is because we need all 30 slips to be possible. Okay, and then we are assuming that everything is equally likely to be picked and that we're picking at random. So what I want you to do is pause the video. I want you to first find what A and B are so you can actually calculate the probabilities. Go ahead and do those probabilities, okay? And then when you're ready, unpause and you can see what I got. All right, folks, let's take a look. So first, let's start by listing out the sample space. So the sample space is 1, 2, 3, 4, 5, 6, blah, 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 all the way up to 30, right? Those 30 slips that are in that hat. Okay, we now need to figure out what A and B are. So A is the event of getting the first 10 students. So that would mean you'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. You're one of those first 10. So then B is being a multiple of 6. So it's 6, 12, 18, 24, or 30. All right. So basically what I need to do is I need to calculate a number of probabilities based on what we've just figured out here. And remember, it's going to be very closely related to the sample space and the event. Okay, those are two very, very important things that we really want to think about. So, first, I want to think about the probability of A, right? That's going to be important. So, if we're thinking about that, we want to think about first, what's the number of elements in A? And that is going to be 10. And then we want to think about the sample space. Well, there's 30 things in there. So it's 10 out of 30, or 1/3. Okay. What's the probability something's either an A or B? Well, if we look at A or B, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we add 12, 18, 24, and 30. So we have these 10 plus those additional 4. That would be 14 out of 30, or 7/15. Okay, when you intersect A and B, what you get is the only overlap is 6. So that would be 1 out of 30. Okay, and the complement. Well, what's the complement? Well, there are 10 things, 1 through 10, that are in A, right? Okay, so if we think about this, that means that there are 11 through 30 are not in A, and that is 20 things, right? 20 things are not in A. So the chances of getting something that is not in A is 2 out of 3. Okay. So now let's think about this. One thing that's interesting that I noticed about probability of A and probability of AC. Take a look at that 1/3 and that 2/3. What do you notice about this 1/3 and this 2/3 if I add them up? They're going to add up to what? They're going to add up to 1. And that's something that's really interesting. So the probability that something happens plus the probability that it doesn't happen appears to be equal to 1. And that is true. That is something having to do with the event and its complement. And this gets at a whole nother way that you can calculate probability. So, if we think about it, first, if you add up the probability of an event and its complement, you're always going to get 1. But what you can do is you can manipulate the equation as follows. You can subtract something from both sides, right? So if you want to know the probability that something doesn't happen, you do 1 minus the probability if it does. If you want to know the probability something does happen, you do 1 minus the probability it doesn't. So again, I'll just sum to you what this means in words. The probability of event A happening is, right, the is the equals 1 minus the probability of it not happening. And when I think not, I think A complement. So how would this be used? Let's take a look. So you roll a blue number cube and a white number cube, and we're assuming these are 6-sided dice. So what are the probability that you do not roll doubles? You do not. So when you think not, you think A complement, right? So let's think A, I'm thinking let's A be, well, you could think complement, but actually, what if we define it like this? So what if A is the probability you don't roll doubles, and A complement is the probability you do? So here's why we're using complement. They want the probability of not rolling doubles, but the reality is the probability of rolling doubles is easier to pick out than the probability of not rolling doubles. So what we're going to do is we make a table of all the possibilities, as you see here in step 2. In step 3, we just choose the doubles. We want the ones that aren't. So we choose the ones that are these 6, and then the 30 of 36 that are remaining are the ones that are not. That's another way to think about it, right? If you have 36 total and 6 are not the things you want, then the remaining 30 are the things you want. So we start with our 6 out of 36, giving us a 6th, the things we don't want, and then we take 1 minus a 6th to get the things we do want. So you're significantly likely to not roll a double. Let's take another look. So I've got another game for you. This one's called 6 or Nixed. So you pay $5 to throw 2 dice. If the dice end up add up, it shouldn't say add up, my apologies. It should say add up. If the dice add up to a number greater than or equal to 6, you lose. Otherwise, you win. So let's take a second and see if we can figure this out. So I'll make my dice table. So this is how it could look. And matter of fact, this is going to take an awful long time. So I have another idea. Let's go back. Let's get creative here. So here's what I'm going to do. I'm going to grab these. I'm going to bring them over here. Okay, so here's our possible results, right? And let's forget what I've circled in black for now. Forget that. I'm going to circle these in red. So which ones add up to a number greater than or equal to 6? That's a lot of them. Look at all these. So I'm going to choose the ones that are less than 6. So for example, 1 and 1, less than 6. 1 and 2, 1 and 3, 1 and 4, now I'm done. 2 and 3, 3 and 2, 4 and 1, 3 and 1, 2 and 2, 2 and 1. If I go beyond there, everything's going to add up to 6. Actually, 6 or more. So this is less than 6. So how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 36 is equal to the probability of less than 6. So therefore, 1 minus 10 over 36 is equal to the probability of being 6 or higher. So what do we do with this? Well, that's 36 minus 10 over, because this is 36 36ths. So we get is 26 36ths or 13 18ths. So you can see I'm doing it now, even starting to do it in terms of a fraction, but you can also feel perfectly free to convert it to a decimal as well, or a fraction, or rather a percent. So if you do it as a decimal, it's about 72% chance. Now, where does this tragically come up is, are you being scammed? This is my last little example, and then that's it for today. So, are you being scammed? So, this is something that happened to me in my life. So, basically, someone comes up to you. You're at like maybe Six Flags. That's where I was. Or maybe you're at another event. And there'll be these people here who look very, very legitimate. And they have a spinner. And they say, we've got 12 equal sectors here, right? So they'll tell you, look, spin this sector. If you spin and you get a blue or an even number, and please note, blue means there's a dot, blue dot. If you get a blue or an even number, you win a trip for anywhere in the world. Now, it seems alluring, right? But first of all, let's step back and take a look. If I'm you and she just offers me an even number or a blue number, should I be skeptical? Well, let's take a look at the word she's using. First of all, she said or. She didn't say and. So what are the blue or even numbers? Blue or even. I'm going to use the U to mean even. Okay, so 1, 2, 3, 4, and 5 are blue. And then 6 is even, 8 is even, 10 is even, and 12 is even. So these are the blue or even numbers. And so that is 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 possible sectors that are good out of 12 possible sectors the spinner could land on. So that's a 3 out of 4th or 75% chance. So what they're saying is you have a 75% chance of winning this trip. Now, I'm going to tell you something. If someone offers you a 75% chance to win a trip that is likely worth hundreds, if not thousands of dollars, yes, you should immediately be skeptical because nothing good is generally free. This scam, I guess, in a sense, is so ridiculous that I've spun it on odds that are similar, lost, and been offered to spin again. Which, when you think about it, is highly ridiculous. So, in any case, what they'll tell you is, in order to get this, they'll say, congratulations. Now, we just need you to come out to our Massachusetts office so that you can attend a presentation, and you will need a $40 deposit. And they'll send you to this presentation on timeshares where they'll bore you to death and throw you through all kinds of loops to give you this vacation, which you may never actually get. So thank you for watching, folks. I know this has been a long video, and I really appreciate your patience. What we need to get out of this is a few major things. One, we need to extract some of the key vocabulary here. What sets are and elements, the empty set and the universal set, and how those things relate to each other. We also need to understand how sets relate with regard to subsets, intersections and unions, and complements, right? We have to have an understanding of what theoretical probability is in terms of the event space over the sample space, remembering that we can actually write the probability as a decimal, so it is okay to write it as a decimal. And then lastly, we need to understand how to execute some examples. So like this gambling or using the complement and working backwards. So again, thank you very much for watching. Please feel free to subscribe or like to my channel so that you can get the most updated videos at all times. And feel free to reach out anytime with questions. I'm available for our weekly hangouts and for open office hours as well. Best of luck, everyone. Don't forget to love math, and remember, you can do it. Until next time, have a great one.